All right, part one is called mechanics, and it's going to be on Newton's first law of motion. All right, so when we look at the history of science, we're going to run into Aristotle and we're going to run into Galileo. And a couple of times throughout this course, Aristotle's going to kind of get bashed here. And before you get all riled up and upset, let me start with the disclaimer that, yes, all science is based on Aristotle. He was kind of the first guy who really thought that the world was logical and understandable. Prior to Aristotle, things seemed random, kind of like the gods created lightning and, whatever. Things were kind of scary and random. And then you had Aristotle who thought, things could be understood, logically understood. The problem was he really thought they could be understood just by using logic. He was a great logical thinker. And the way science is sometimes that what we think is true, you have to actually go test it and see if it's true. And unfortunately, Aristotle didn't really ever go test his stuff. And so a lot of it ended up being wrong, but because he was so great in so many other ways, people just assumed it was right, like for thousands of years, like for 1,500 years or something. They just kind of thought he must be right because he's so cool. He was wrong on some of the science, right on the idea that the world is logical and we can understand it, but wrong on the specifics. Okay, so how was Aristotle wrong? Let's look at that first. How was he wrong? First of all, he thought every object had a quote-unquote natural state. And he would look at sort of natural versus non-natural states and violent motion and this kind of thing. And this idea that, well, naturally things want to be on the ground, like a boulder wants to be on the ground, so it tries to naturally go there. And heavier object must, sort of really want to go there. Okay, well, we now know that's wrong. That's not why things fall. But he just thought about it and kind of assumed that was correct. All right. Let's go to why he's wrong, part two. We had this idea of this unnatural motion, all right? So things might naturally want to be there, but then maybe there was this unnatural motion, and he called that violent motion, like it's not supposed to happen. And then if you stopped this violent motion, this pushing or pulling, then things would revert back to their quote-unquote natural state and stop moving. We now know, friction just stops the brick from moving. It would actually, in outer space, it would actually go on forever and ever and ever. But here on Earth, we have friction and air resistance and things that stop it, and so there are forces acting upon it. Aristotle didn't ever test this, so he thought there was just, the natural state was for the brick to be on the ground, not moving. Okay, another example of Aristotle thinking about things and actually getting them wrong is, and without high-speed cameras or anything, they couldn't look at sort of how things fall kind of parabolically. And he literally thought that the cannon would go straight, and then it would fall. It would stop, and then it would fall. I mean, we now know that absolutely not. It follows a curve, right? When something falls, the motion doesn't go straight out and then straight down naturally. That's not the way it happens. All right, so Galileo came along and actually started testing these ideas and, famously dropped things off the Leaning Tower of Pisa and dropped two balls of different sizes. Now, didn't drop a feather because, again, we get it into air resistance and things like that. But he dropped two weights where air resistance would be very minimal and found out that, in fact, they fall at the same speed. So this was experimental data. This wasn't just thinking about things in our head. Galileo actually went out and tested this. All right. So Galileo has more tests that he did, and he actually did a series of tests. Obviously, things going downhill, the speed increases, and then uphill, they'll slow down. And on a flat surface, it would be constant if you had a really heavy ball and no friction. We know over time on Earth, we have friction. We just have to deal with that. So hypothetically, that could be a constant. In reality, it's going to decrease slowly. But either way, the point is that this goes against what Aristotle said, all right? You know, the idea that the natural state on Earth is of not moving, that's not the case. And he actually did a series of inclines, and what he found was that, you know, if you got a heavy ball and you could kind of minimize your resistance here, your friction, the initial position, the height would be the same as the final position. Think of a pendulum swinging here. It goes up just as high as on the one side as where you released it, approximately. Now we know, again, over time, that's not going to happen. Eventually it's going to stop, but at least for the first roll, it's going to go up. Again, this questions the natural state, okay, of things. All right, Newton's first law of motion can be stated: an object at rest remains at rest, and an object in motion remains in motion. And then there's the asterisk, unless a force acts upon the object. And so we don't see this on Earth very often, where you push a boulder and wow, it just goes forever. Again, we have friction, we have air resistance here on Earth. But you could see it in outer space. You could push something and it would go on forever, literally. And we know that things are at rest, remain at rest. I mean, if you're sitting here right now in front of your computer, you know, or your little, whatever, iPad you're watching this on, and it started floating off and moving to the right, you would be like, wow, there has to be something going on here. It just doesn't do that all by itself. There'd have to be a force. We know that for a motion to occur, you have to push an object or give it some kind of force. So that is stated as Newton's first law of motion. All right, so an object at rest, it's not moving. If there's no force, it's just not going to move. If it's in motion and there's no force, it's going to keep going the same way it's been going. All right. A way to think of this is if you're riding in a car, wherever, if there's no force acting on you, if you're just riding along at, even if it's 80 miles an hour, doesn't matter. If you're going, you don't need a force to just keep going. You feel almost like if you're not looking out the window that you're standing still, right? It's only when the train comes to a stop that all of a sudden you feel that force against you. Or if the train tries to accelerate, you'll feel that force against you. But when you're just kind of cruising along and you're in motion, you're just going to stay in motion, right? Again, barring friction. A little demonstration you can do is, you know, and what you're supposed to imagine is all these little carts are stacked on each other and they're moving to the right. Well, that green cart is going to hit the wall first. There's a force on it. It causes it to stop. It changes its motion due to a force applied to the green block. But the blue block hasn't hit it yet. So again, no friction in this world. It's going to continue moving to the right until there's a force acting on it. And then it would stop. And then lastly, the red block would stop last when it hits the wall. But they would not stop unless you applied a force to them. Okay, the classic tablecloth demonstration, the magicians, you know, take the tablecloth and yank it really quickly. That has everything to do with the first law of motion. That whatever is on there is at rest. It is not going to move unless you apply a force to it. The only force you're applying is whatever friction is on that tablecloth. So if you notice when people do this, they tend to do it with those kind of shiny polyester type tablecloths that aren't really bumpy and friction. You never do it with a weave or anything like that because you'd have too much friction and you'd screw the whole thing up. But again, anything on there is going to stay where it is until a force is acted on it. You're going to get a little bit of friction there, but if you do it quickly, you can actually do this. Okay, yeah, we had questions about toilet paper. You didn't even know you had questions about toilet paper until you started taking physics. See, we're going to answer one of those burning questions in life. Why is it when you yank the toilet paper of the little roll, it just keeps rolling and rolling and rolling and ends up all over the floor? And it doesn't happen with the big roll. Okay, why? Well, ask yourself, which one has more inertia? Which one is harder to move, right? When we talk about inertia, we're going to talk about which one is more difficult to move. We know a heavier object has more inertia. It is harder to move it. That means that big roll of toilet paper is harder to move than the little roll. So the same yank, and we all know what happens. Okay, we're going to talk about a support force. We're going to see more of this a little later on. But a support force is what's going to hold anything up. And if it's perpendicular to the surface of something, we're going to call that force the normal force. And in this case, normal is just going to mean perpendicular to. No, I don't know why we use the word normal for perpendicular to. We just do, so just memorize it because you're going to see it a bunch of times for the rest of the year. But a support force is anytime you have a book, it's going to fall unless you support it, right? Or your computer that you're watching needs to have something supporting it. And that will be equal to the weight of that object. So when we look at the weight of something, if it weighs 100 newtons, which is, you know, a fair amount, you would need 100 newtons of support force to hold that gold brick. Otherwise, your table would break and the brick would fall. If you want to think of newtons kind of like pounds, they're the international system, the same as pounds. So if you think of it like you have a 100-pound brick, you better have 100 pounds worth of support holding it up or it will fall. All right, so when we look at forces, we need to add them all up. Okay, we want to take all the forces and we want to add them all up, and then we get what's called the net force acting on something. And so if you are pulling something to the right with 10 newtons and you're pushing it with 10 newtons or something, you would add those up and get 20 newtons. Or if you're pulling it to the right with 5 and you're stopping it with 5, you would get 0. All right, so if we look at our little example down here, and you're going to see more of this again in later chapters, but if we look down here, this has 5 newtons getting pushed to the right and 5 newtons. Think of it, 5 pounds of push to the right. Those net add up to 10 pounds to the right. If somebody's pulling on it with 5 pounds this way and pushing on it with 5 pounds that way, that's 0. That block isn't going anywhere. That's the net force on it. It's just staying right there. All right. We're going to start a little bit with vectors in this unit. We're going to hit vectors more, not with linear motion, but with the next unit after that. But you need an introduction to start thinking about the inertia here. So we're going to just hit vectors a little bit, and we're going to continue on with vectors. All right, so what is a vector? Vector has magnitude and direction, all right? So scalars, what we call scalars, just have magnitude. They just tell us the size of something. A vector has to have a direction going with it. So a little later on, I'm going to ask you, well, what's the difference between speed and velocity? And one of them is a vector quantity, and one of them is a scalar quantity, all right? And vectors we can represent by an arrow. And examples of vector: velocity, force, acceleration. Those are things that are vector quantities. That we can give them direction, okay? When we go to draw these arrows on our paper, we're going to have to be careful about how long we draw those arrows, because that length is actually going to represent the magnitude of that vector. So there's actually some math involved in this. We're actually going to measure the length of some arrows to see how big those vectors are. So we don't just draw these randomly, you know, arrows flying everywhere. We're going to be careful with the size of our vectors. Okay, when we do vectors, all right, a vector is the sum, the resultant is the sum of 2 or more vectors. So resultant just means we're adding up some vectors. So if you're adding up 2 vectors in the same direction, you add them arithmetically. You just literally, you add them. The previous example of we're pushing a block to the right and we're pulling the block to the right, they would just add up going to the right. If the vectors are in opposite directions, you subtract them. So when one was going to the left and one was going to the right, we subtracted and it came out to 0. And then if 2 vectors act in the same or opposite directions, you can use a parallelogram rule. And we're going to talk about how to do head-to-tail vectors. We're actually going to do some examples. And then 2 vectors at right angles to each other. Most of your vectors for physics are going to be at right angles. Not all of them, but most of them can be done at right angles. So yay, Pythagorean theorem. I will show you shortcuts on that. All right, so let's look at this vector. We have a block, and instead of getting 30 newtons to the right and 40 newtons to the right, which would just be this lovely 70 newtons to the right, we actually have 30 newtons up, and we have 40 newtons to the right. So let's look at some statements we can say about this. Okay, the 50 newtons is the resultant of the 30 and the 40. Is that true? Is this 50 newtons here the resultant, right? And the answer to that is yes. If we were to, what these are, these 30 and 40, is we have taken apart this 50 Newton thing. We can actually imagine this is a block and there's a kid with a string pulling on it with 50 newtons of pounds this direction. We can imagine that. It would be 30 newtons worth of force up, lifting the block off the ground, and 40 newtons along the carpet in that direction. We can actually take those two vectors apart. All right. So let's look at B. The 30 Newton vector can be considered a component of the 50 Newton vector. Absolutely, I just said that. This is the y component of this vector. When we take it apart, we'll call this the y component. The 40 Newton vector can be considered a component of the 50 Newton vector. That's C. Absolutely, this is now the x component. We can literally take this apart, and what it does is it makes it mathematically easier for us. We have this 50 Newton vector kind of going off into outer space, and we can look at it nicely in these two little lines, you know, nice x, y coordinate type things. Makes life easier for us. Okay, so that's all of the above are true for that one. All right, so let's take a look at why we need vectors when we look at you know, anything with inertia. So we have a kid here hanging from a rope. And the question is, if you had to hold the rope, if you were either going to be a person here holding the rope, if you're either going to sit here and hold this rope, or you're going to sit over here and hold this rope, where do you want to be? And hopefully you can look at the picture and kind of logically figure out, well, what the heck, I want to be over here. This person has less weight on them than this person. If she was right underneath this hook, all the weight would be on this line. So one way we can do that is literally look at the vectors of this. Now she is getting pulled down by gravity here, okay? And we're going to fight that pull of gravity with these two ropes. But each of these ropes is also pulling out. So we're only concerned with fighting her gravity. We're only concerned with this one vector. So let's look at the next slide, and you're going to see how we can use drawing of the vectors to figure out which one has more tension on it. All right, so here we go. We drew the vectors. And you can see on B, right, let's look right here on B, you can see that this vector is a lot longer than this side, all right? And so literally by the length of it, this is longer. And again, remember I said we're not going to like randomly draw lengths here. This length actually means something. Vector quantities means that this number here has a meaning, all right? This is longer than this one. That tells you that this rope is more tension on it than this rope. This one's shorter. See, this direction is shorter. And the parallel thing means that we're going in this direction for this one. That means this one has less tension on it. All right, and then when we look at things pushing and pulling on different objects, what we're going to say is if that object isn't moving, then when we add up all those forces, they better equal 0. So if I'm pushing on a block from the left and I'm pulling on the block from the right, and you know it's sitting on a table pushing down and the table's pushing back up on it, in every direction we look, it should equal 0, all right? Now, things can be moving, and believe it or not, the equilibrium can still equal 0 as long as they're not changing their speed. And we're going to get a little more into this, but you have to think of an outer space for this one to make sense to you. If things are floating away in outer space and they're floating off, it can go on forever with 0 force, a net equilibrium 0 force on it. And only if we want that to change, only if there's a change in that motion, then we know that there's an applied force somewhere. So on Earth, you can see the little picture. Usually the force acting on it, we almost always have to factor in friction. We live on a planet, there's friction. There's gravity, there's friction. But if you were thinking of something in outer space, there'd be no friction. It could move on forever in equilibrium with no force, net 0 force acting on it in all directions, and it would just keep moving. When it moves, either to the left, to the right, stopping, speeding up, or anything like that, any change in motion at all must be done by a force.